Many of the concepts and models used to explain past caldera-forming eruptions and subsequent collapse were formulated by USGS scientist Robert L. Smith and his colleagues, primarily based on their work at the Valles caldera in New Mexico. Subsequent research by USGS scientist Peter Lipman at a tertiary caldera in the San Juan Mountains in Colorado shed light on many of the fundamental processes that link large-scale eruptions and caldera collapse. Geologic mapping by USGS scientist Bob Christensen suggests that the collapse of the Yellowstone caldera 631,000 years ago was a response to the eruption of about 1,000 cubic kilometers of magma occurring within hours or days. But recent field observations suggest a more complex story about the eruptions that formed the large caldera. We can learn more about past volcanic eruptions and caldera collapse from observations of more recent eruptions. The 1912 Novarupta eruption on the Alaska Peninsula was the largest of the 20th century, with a volcanic explosivity index score of 6. There were numerous eyewitness accounts of the eruption, including observations made several years later by Robert Griggs. Approximately 15 cubic kilometers of magma erupted over a 60-hour period. An interesting observation was that the caldera did not collapse beneath Novarupta, but rather that magma spread laterally from beneath Mount Katmai, about 10.6 kilometers (6.6 miles) to the northeast, and collapsed due to lateral drainage from its magma chamber. In unraveling the details of the Novarupta eruption and the geologic history of the region decades later, USGS scientists Wes Hildreth and Judy Fierstein were able to use eyewitness accounts. And in contrast to the geologic mapping at Yellowstone, they mapped a less eroded landscape and less altered rock. In the late 20th and early 21st centuries, the establishment of a volcano monitoring network allowed scientists to capture several caldera collapses in unprecedented detail. A prime example of this is the 2018 eruption of Kilauea volcano on the island of Hawaii. Data collected with seismometers, tiltmeters, high-speed global positioning system, GPS, stations, and gas sensors helped document the precursory activity, caldera growth, and subsurface lateral magma transport from Kilauea's summit to the eruption site in the volcano's lower east rift zone, not unlike what had occurred at Katmai and Novarupta 106 years earlier. In the 3 months following the eruption, the caldera at Kilauea's summit shrank by more than 500 meters. Many types of monitoring instruments captured the onset of subsurface magma transport, the geometric development of the receding caldera and its faulting, and the amount of magma erupted during the collapse of the Burrarbunga caldera beneath the Vatnajökull glacier in Iceland in 2014-2015. As at Katmai and Kilauea, magma spread laterally beneath the surface away from the caldera, erupting 1.5 cubic kilometers of basaltic magma at Holaron, about 40 kilometers to the northeast. Other 21st-century caldera collapses recorded by volcano monitoring networks include the collapse of Miyakijima volcano in Japan in 2000 and the collapse of the Dolomieu crater at Piton de la Fournaise volcano on Réunion Island in the Indian Ocean in 2007. Because of the increasing capacity to monitor volcanoes from space, Even the 2018 caldera eruption and awakening, unlike the collapse at the remote Sierra Negra volcano in the Galapagos Islands in the Pacific Ocean, was documented in great detail by a variety of instruments. The ability to capture and document caldera collapse with modern monitoring networks provides scientists with a wealth of data to refine the initial models proposed by Smith, Lipman, Christensen, and others. Although a large caldera-forming eruption such as the one that resulted in the Yellowstone caldera has never been witnessed, geologists can use modern examples, coupled with insights from the geologic history of the Yellowstone region, to better understand how caldera collapse occurs.